In this last video, we are going to discuss another abstract data type, which is the queues. I'm not going to go into in-depth in the queues because you have already seen stacks and queues in your previous courses, which is Programming Fundamentals 2. But I'm going to give you an overview or kind of like a refresher. And as you saw in the previous set of videos, I went into stack for more depth. So I'm going to leave it up to you. I'm going to just discuss more conceptually what queues are as well as where they can be used. So let's get started. So a queue is a data structure which follows the principle of first in, first out, which is different from the stack. Like while stack was last in, first out, a queue behaves like a regular queue that you see in your real life, which is like, let's say if you all are going to into a flight, uh, you make a queue and you try to like whoever comes first goes in first and so on. So the QADT, when we talk about QADT, it behaves quite similarly to the stack. There's one addition, which is like when we talk about the data, when we were discussing stacks, there was just like this items and the number of items. In queues, apart like there's no top, there's going to be two different data members, which is going to be front and back. And how queues look like is like you have this array where you store some numbers. So the front points to the front element, which is the first element, and the rear points to the last element. The operations that are supported by the QADT include enqueue operation, which is basically equivalent to the push operation on the stack. It adds an element to the back of the queue. So whenever we are adding something at the back, we need to update the rear pointer. When we talk about dequeue, it removes the element from the front. So in that case, we update the front after removing the element to some other position. The size returns the number of elements stored, and isEmpty returns whether the queue is empty or not. So again, like when we are talking about the implementation, you can implement queue in the form of an array. Now let's call this as class queue array. The private variables for this class would be, like since it's an array based list, it will be of course an array of again like max size, which we discussed in stack. Now instead of just a top position, we'll have like two pointers or two indices that store front and back. And how queues generally work is like whenever we start, you can have these indices. Like actually it doesn't matter. Whenever front is equal to rear or back, like you can call it anything, like I'm going to call it front and back for consistency. So then we know the stack is the queue is empty. So let's say if we are trying to implement the empty function, this is the condition we are going to use. And whenever we have some element in the queue, like let's say if I do something like enqueue 5, so for the initial case, like both front and rear is equal to 0. Like we say that both front and rear are here. Now whenever we enqueue 5, only like based on our previous interpretation, let me go back. Like whenever we are in queuing, we only changed the rear element, not the front one, because now if we do 5, front still remains like 0, but rear is updated to 1. So basically what we are trying to say is the rear will always point to the next position where the element needs to be inserted. Like currently it's not pointed to 5, but it's pointing to the next one, and we need to maintain this gap because otherwise we will not know whether the queue is empty or not. Now one big issue with this implementation is that Like let's say if you repeatedly remove like let's say let's do one more operation, like let's do dq. So if we do dq, we are going to just manipulate the front operation. So in this case, the front index would now be incremented to this one, and rear will remain the same. So again, like if I do a dq, I'm going to remove this number. So I have this array. I'm going to remove this number. Front will now update to the next position and rear will now update to the same position. So in this case, again, like if front is equal to rear, we know that it's empty, but you can see that like if we do this repeatedly, we are moving these pointers again and again to the end. And there's no way to check like whether we reach the size or not. And this gives rise to something called rightward shift problem. There's a question on Stepic regarding it. Definitely try that, which is like, let's say if we do n elements or n queued and then n elements are d queued, we'll basically reach the end of the list. Both of these are pointing. Although this array is empty, the issue is it will behave as if the array is full. And if you need to insert more elements, you need to go back and it's going to be a mess. So how we conceptually represent this queue implementation is through something called a circular array, which we are going to discuss very soon. But let's discuss the trade-offs of the implementation in the form of array. So the characteristics of this kind of implementation is again very similar, which is it has fixed size, it stores similar elements. Now we access through the front instead of top in stacks. The operations supported are enqueue, dequeue, size and is empty. If we are enqueuing, dequeuing, or checking the size or is empty operation, it's again going to take constant time, because again we don't want to traverse any loops here. We are just manipulating or incrementing the front plus plus or like a rear plus plus or rear minus minus or front minus minus in certain different scenarios. I'm not going into the depth of like how to implement each functions. Again, like there's a lot of resources, you can look into the book as well. It's very easy, like it's not too complicated. So all the performance would be like O of 1. The benefits of this approach is again like we can uh, use all the operations in constant time. While the drawbacks is again like it has limited space as well as this rightward drift problem, which is I mentioned like at if we do n insertions and then n dequeuing operations, the list behaves as if it is full, but there's still like always there's all the list is empty, but we have moved the pointers to the later half or the last element in the array. So how we can fix that is by using this circular array representation. And how this works is you can use the modulus operator, which is if you have this front and rear values, and if you use mod operations on this followed with the max size, you can wrap these elements, which is you have these two variables f and r, which keeps track of front and the rear element. In this normal configuration, this front and rear, you can see it's moving, but in the wrap around configuration, you can see even if the front is on some x position, rear might be in a position which is less than f. Like in the normal configuration, rear will always be more than f. There's no way that it can be less than. So it is going to be either equal to or more than that. But in a wrapped around configuration, since you use the mod operation, whenever like r reaches here, the next r will, like let's say if we try to add another element at this position, so in that case a new element will like r will be r mod size, and now we are already at the size position, right? So it will be size mod size is 0, so it's going to insert a new element right here. I'm not going to again like go into depth for this. We have given you solution, to a stepic problem, try this one out. It's a pretty interesting problem, like how to wrap around the numbers. So basically, you have this front and back for, like, this is one instance of the queue. Like we have it as in the form of array, but instead of looking at the array in a linear or straight rectangular fashion, we are just going to wrap this around so that we see this more like a circular array rather than a straightforward one. So if you do a DQ here, we are going to like remove, like as I told you, when we do a DQ, we increment the front, and if we do an NQ, we increment the back one. So in this case, we have incremented the front. Now in this scenario, like this one, we have again a DQ operation. So we have again incremented the front to point to the index 2. Now if we do 12, like if we NQ 12, we are going to increment the back pointer. You can see this again, like try to see the solution for this code. We are not going to discuss this in the problem solving lecture because we have more problems to discuss. But this approach solves the third issue, which is the wraparound one. So it again has the same constant amount of operations. Like for all operations, it take constant amount of time. It again has a drawback of limited space. But now at least we have solved the right word drift problem. The next approach is the linked list based approach. So in this case, you have this class called queue underscore linked list, and now you have a node pointer. And in this case, we need two different pointers. The first one is the front, and the second one is the back or the rear. So this front one is now equivalent to the head of the linked list, and the back one is equal to the tail of the linked list. Also, there's going to be two different private variables, which would be node star next and data that will store the actual data. And again, like the operations are the same, NQDQ, you're just manipulating the pointers. Initially, like when we start, both head and null, sorry, head and in this case, front and back. So we have front and back, they both point to null. Now let's say if we do NQ5 in a linked list based queue. So how it's going to work is it will create a new node. Now the head will now, or the front will now start pointing to this new node. And since the back is also null, both front and back will now point to this new node. Or basically the new nodes next would be back. Now if there are two elements, like let's say if we try to do again like NQ6, we are going to add the element right at the end of the linked list, not in the beginning, which is you have 5. So now 5 will point to 6. And the rear one will now be pointing, or the back one will be pointing to the back of the linked list. So again, like I'm not going into depth for this, but basically the rear will always point to the last element in the list, and the front one will point to the first element. And as we like insert or delete elements, we are manipulating the pointers. So again, the characteristics of this approach is now we have a flexible size. Operations will still take like O of 1 time. The drawbacks is it's taking more memory because we now have like two more pointers that are storing the values, which is we have this next pointer as well as the tail pointer that will be required to store the index of the tail. Now the queue is implemented in STL. Again, It has like four different operations. I've shown you the reference. You can go to the link and check it out. The enqueue operation adds an element to the end of the queue. Dequeue deletes the first element of the queue. Empty returns whether the queue is empty. And finally, the front and back are two operations which return either the first element of the queue or the last element of the queue. This is another stepping problem which describes whether a queue is valid or not. Uh, I'm again for the sake of time, I'm not describing it in detail, but basically we have a queue of numbers that has some ascending values, and we are going to check whether this queue is valid or not. So you can define a queue with the same syntax as stacks. Again, I'm going to discuss this problem in detail in the problem solving lecture. So some of the use cases of the queues include, like in real world, we see like buying tickets or the drive through fast food chains, as well as the appointment systems at our dentist and so on.